chapter 6, I feel like, is memorizing all the properties that go with each individual polygon. We're going to start with 6.1, which is going to talk about any kind of polygon. And then after we get done with 6.1, 6.2 through 6.6 are going to focus on just the quadrilaterals. How many sides does a quadrilateral have? 4. So we're going to focus on just the shapes that have 4 sides. And we're going to get very specific about them and talk about each shape and exactly what properties it has. And you're going to have to memorize those properties. Okay? So that's the hardest part. So you've got a separate sheet of paper today, because what I have found helps the most is for us to go through this chapter and create a properties sheet as we learn them, separated by shape, and then at the end of the chapter you'll have this great piece of paper with all your properties as a study guide. Okay? Feel free, if you like to color coordinate things, get out your markers, your highlighters, your colored pens, whatever you want to do. 6.1 is going to have 4 formulas in it that you're going to need to memorize, and so you may want to add that on this sheet as well, even though they're not properties. You may want a little subsection of just formulas, but then once we hit 6.2, from then on, it's going to be, here's a shape, let's list its properties. Here's a shape, let's list its properties. If you know the properties, the math in this chapter is not hard. It's just going to be deciding, what do I do with these simple algebraic expressions? Do I set them equal? Do I add them? What do I do? And then solve. Yes, there will be some proofs, and there will also be solving with quadratics, so it's not going away. If you cannot factor or use the quadratic formula, get in here and let me help you before the next test. But you'll see problems again where you have a quadratic and you have to set it equal to 0 and you have to solve. Okay? So super important. All right, so we're going to start with 6.1. 6.1 is the easiest section. It is just general information about all polygons. It's really thick because there's a lot of simple examples. So we'll go through it pretty quickly. So first of all, just some vocabulary. When we talk about a polygon, remember that we said a polygon is going to be many-sided figure. It's going to be a closed plane figure. We defined this word a while back. It has to be closed. It can't be open. It has to be made up of segments. So circles are not polygons. They have to intersect at the endpoints. You can't have part of it going on forever in another direction. So we're dealing with polygons. They have many sides. And when we talk about the side, we're talking about a segment. So if they ask you to name a side of your polygon, you're naming a segment. Like, for example, AE would be a segment, which is a side of our polygon. When 2 sides meet, we call that a vertex. What's our plural form for vertex? Vertices. And so this shape would have 1, 2, 3, 4, 5 vertices. Not vertexes, yes, vertices. And then, yeah. And then a segment that connects 2 vertices that are not consecutive. So if I go from A to B, that's consecutive. That would be a side. If I go from B to C, that's consecutive. That's a side. If they're non-consecutive and you connect those 2 vertices, like B to D, that's going to create a diagonal. Okay, so there's lots of diagonals in this picture. We could go from B to E. We could go from A to D. We could go from C to E. We could go from, what have I missed? I got B to D, C to A. Oops, that's terrible. C to A. Yeah, except mine's a little, like I got a hammock or something hanging out there. All right, so you could connect any 2 non-consecutive vertices and create a diagonal. Yes, sir. Triangles would not have a diagonal. Correct. All right, so just some vocabulary there. These are the names that you are going to be required to have memorized. You must know these types of polygons. So a triangle is 3 sides, quadrilateral 4 sides, pentagon is 5, hexagon 6. Be careful when you spell heptagon. It's H-E-P-T. So heptagon. 8's an octagon, 9's a nonagon, 10's a decagon, and 12's a dodecagon. Anything above 12, we'll just write, for example, 13 would be a 13gon. 17 would be a 17gon. So we'll just call it an n-gon, and we'll plug in whatever number of sides it has. Yes. Everybody asks me every year about 11, and so again, these are the ones you're required to know. If you flip over to the next side, 11's called a hendecagon. 12's here, but you are required to know 12. It's on the other slide. And then everybody asks me, so I went ahead and just clipped this and put it in your notes. You can Google, there's a name for every sided shape out there, but uh, Hecatomyriagon. Hecatomyriagon. You don't need to know any of these. I've never had to know them, but I've never used their names. I mean, we've talked about the shape or how many sides might be in a problem, but okay. Um, Heptadecagon or heptachidecagon. Yeah, yeah. Enneadecagon or a nonadecagon. All right. So these I just wanted you to be aware of, but again, you don't have to know these. Hendecagon, I don't know why it's not a big deal, but we don't use that very much. These are the ones you have to know. So make sure you know those. I will give you problems where I say dodecagon and you have to know that means there's 12 sides. Okay, so it's super important that you know those names. All right, so just for your curiosity, there's that table. I already said this once just a minute ago, but just a reminder, a polygon has to be closed. It's a two-dimensional figure. It's formed by segments, and they have to intersect at the end points. Okay, so we talked about a few chapters ago that something like this is not considered a polygon. Something like this is not a polygon, and circles are not polygons, so it has to fit that definition. Okay, and then it's simple. Tell whether the figure is a polygon. If it is, name it by its number of sides. So is this a polygon? And what's it called? Hexagon. And again, we're going to go pretty quickly, so you may want to write. It's your choice, your notes, but yes. So we're going to go pretty fast. I put a lot of examples just for practice here. Is this a polygon? Yes, it is. It meets the definition. How many sides does it have? What's its name? Good. Heptagon has 7 sides. H-E-P-T, heptagon. All right, what about the next one? Is this a polygon? No, why not? It has curves. It's not made up of line segments. So it is not a polygon, therefore it does not have a name based on its number of sides, because some of those are not sides. What about this one? Nope, it's not closed. All right, so then we go to the next definition, which is regular polygon. Got it? All right. Regular polygon. So first of all, just some reminders of vocab you already learned. If it's equilateral, that means that all the sides are congruent. If it's equiangular, remember no L. Equiangular, all the angles are congruent. And so now this chapter, if it is both equilateral and equiangular, we call it regular. Regular is both equilateral and equiangular. Okay, so we had a shape that we learned before that if it was equilateral, it was automatically equiangular. And if it was equiangular, it was automatically equilateral. What shape did we learn that about? Triangles. So a triangle, if it is equilateral, is regular. And if it is equiangular, is regular. Is a quadrilateral going to have the same property, that if it's equilateral, it is definitely equiangular and vice versa? No. What is a name of a quadrilateral that is only equiangular? Square would be regular. Rectangle. A rectangle has 4 right angles, but it does not have 4 congruent sides. Right? What's the name of a shape that has 4 congruent sides but not 4 right angles? Rhombus. And then the joke for the day. Why was the student late to school? He was on the rhombus. I know, it's really bad. All right. No, but it popped up the other day, and I thought, I need to remember this when we get to chapter 6. So, all right, so 4 congruent sides could be a rhombus, 4 right angles could be a rectangle, so you can have a quadrilateral that is only equilateral, only equiangular, or if it is both and it's regular, what shape is it? A square. So a square would be the one that is both. But a triangle is special because a triangle, if it's equilateral, is always equiangular, which means it's always regular. Okay? All right, I just want to make sure we were clear about that. If it's not regular, the way they say that is irregular with 2 R's. So IRR, irregular. It's not too bad. I'll have to look though. There's a lot in this first section, and then there's not as much as we go on. Okay, so we got regular down. It's both equilateral and equiangular. The next few words are concave versus convex. Concave, the vocabulary word that they give, or the definition they give you for it, is a little bit complicated, so let me explain it. It says if any part of a diagonal contains points in the exterior of a polygon, then it is concave. Okay, so here's what that means. I'm going to draw a picture here. If I were to draw, do you have pictures? Okay, so let me look at your pictures. Okay. So if I look at this picture, if I were to draw in all diagonals, so here's one diagonal, but here's the other diagonal, right? Notice that that diagonal has at least part of it, all of it in this case, outside the shape. So if any part of your diagonal is outside the shape, then we say it's concave. Over here, if I draw in all the diagonals, they're all inside the shape, so we say it's convex. Convex, no diagonal. No diagonal contains points in the exterior. The way I think about it is if something is caving in on itself, it's concave. If it's not caving in, it's convex. So if you think about it as caving in, that makes it concave. But your definition you need to know for the vocab test will be, if any part of your diagonal is outside, it's concave. If all diagonals are inside, it's convex. Just one piece and one part of it. If any part of any diagonal is outside, it's got to be caving in at some point on itself. Does that make sense? Okay. So then there's going to be several examples in your notes where they ask you to decide, is it regular or irregular, concave or convex? So what is this, regular or irregular? Irregular. It's equilateral, but it is not equiangular. So it's irregular. Is it concave or convex? Convex. Okay, it is not caving in. All diagonals would be inside. Next one, regular or irregular? Irregular. It almost looks like it is equiangular, but be careful, there are these big angles here inside as well. And so a lot of times we forget about those. So at each vertex, there's going to be an angle measure. So it's really not equiangular or equilateral. So it is irregular. And is it concave or convex? Concave, because again, if I connect these, my diagonal's outside. For it to be regular, would it ever be able to be concave? No. If it's regular, it has to be convex. There is no way it can be concave and be regular. All the angles and all the sides would not be the same. All right, so regular, irregular. Regular, concave, or convex? Convex. And again, if it's regular, it has to be convex. It cannot be concave. All right, next one here. Regular or irregular? Regular, concave, or convex? Convex. And here, regular or irregular? Concave or convex? Concave. Again, it's caving in on itself, and we have a diagonal that would land outside if we connected them. Okay, any questions on those? All right, so now we're going to move on to these 4 formulas that you're going to need to memorize. And we're going to kind of develop them so you can understand where they're coming from. So first of all, we want to be able to find the sum of the interior angle measures for any polygon. So let's start with the one we already know. What is the sum of all the angle measures inside of a triangle? 180. Okay, if we add all the angles inside the triangle, we get 180. So now if we think about a 4-sided figure, pick one vertex and draw in all the diagonals from that one vertex. So in this case, there would only be one diagonal we could draw, right? How many triangles does it divide it into? 2. So what do you think the sum of all the angles inside a quadrilateral is? 360. It should be 2 times 180, which is 360. Follow that same process. If we go to the pentagon, just pick one vertex. Draw in all the diagonals from that one vertex. It's going to divide it into triangles. How many triangles do we get? 3. So if we do 3 times 180, what's the sum of all the angles in a pentagon? What is it? Close? 540. 540 degrees. Go to the hexagon, same thing, pick a vertex, draw in all the diagonals from one vertex. How many triangles do we get? 4. So 4 times 180 is 720. And we could keep going, right? Depending on how many sides we have. How much do we add each time that we add another side? 180, because we get one more triangle, right? So if we wanted to, we could come up with a formula for how do we calculate the number or the sum of all the angle measures inside any polygon. So if I said, what's the sum inside of a 105-sided figure, you wouldn't want to keep doing this until you got to 105, right? Maybe. But if I said, 15 million, that would not be very fun. So if it has 3 sides, it's going to be 180. So we do 1 times 180. If it had 4 sides, we did 2 times 180. If it had 5 sides, we did 3 times 180. If it had 6 sides, we did 4 times 180. Do you notice a pattern? It's going to be something minus 2. And you could say X, they're going to use a different letter. They're going to use N for the number of sides. But basically, if we take the number of sides and subtract 2, then we get the number that we want to multiply by 180, right? Exactly. So, you got it. We won't go that big, though. So, your formula for any polygon would be n minus 2 times 180. You'll start to memorize, just like a triangle's 180, you'll start to memorize a quadrilateral's 360, a pentagon's 540, just because you'll do several problems and then you'll start to get it in your head. But if you forget, it's not a big deal. Just however many sides, minus 2 times 180. If you've got a calculator, it doesn't have to take a long time to figure it out, okay? Any questions? All right, so that's your first formula that you're going to need to memorize. And here it is. So on your formula sheet, to help you organize that there's 4 formulas, you write down what they're going to be as far as the titles, and then you can fill them in. So first one that you need to have memorized is for interior angles. And if we want to know the sum, meaning all of them, we do n minus 2 times 180. That's the first formula you need to know. If they were talking about the interior angles of a polygon, and we want to know the sum of all of them, we do n minus 2 times 180. Okay, second formula you're going to need to know is what happens if your shape turns out to be regular. And this is only going to be true if it's regular. Regular again means what? Equilateral and equiangular. So think about this with me. If it's regular, all the angles are going to be the same. If it's regular and I want to know one angle, we're still talking interior. I want to know one angle. Sometimes the directions will say find each angle. Same thing. If it's regular, they're all the same, so each means one of them. What would I need to do to the sum if I want to know one angle and I know they're all the same? Just divide it by how many angles you have, which would be the number n. So the second formula that you're going to need to know is if it's regular, I can take the sum, n minus 2 times 180, and divide it by n, and that will give me one angle since they're all the same. And we did that back when we talked about our triangle, when we said it was 180 and then it was equiangular. Each angle was how much? Very good. So 60, right? 180 divided by 3. Okay, so that's the first 2, and that's dealing with interior. So we'll look at some examples, and then we'll talk about exterior angles. So when you're looking at your paper, the next 2 will be talking about exterior angles. And we'll have 2 formulas for it as well. But these are only if we're dealing with interior inside the polygon. So first question, find the sum, look for your keywords, sum of the interior angle measures of a convex heptagon. So heptagon, Alexa said, is 7 sides. So what formula would we use if we want to know the sum of the interior angles? Okay, we start with n minus 2 times 180, and then we plug in 7. What's 7 minus 2? 5. And 5 times 180? 900 degrees. Don't forget your degree symbol because it is an angle measure. Make sure I don't go too fast. Slow me down if I do, okay? All right, next one. What are we looking for? Okay, so what are some key words we need to focus in there? Regular. What else? 16 gone. What else? Each. That's big. And interior. So that tells me I'm dealing with interior angles. It's regular, and I want to know each, which means I only want one of them. So now I'm using this formula. Find the sum, divide by how many you have. So we have n minus 2 times 180, but now we're going to divide it by n because we want to know what each angle is. So what's going in for n? 16 minus 2 times 180 divided by 16. Be careful that you don't do 16 minus 2 is 14 in your head and then divide by 14. I've seen that a few times. So bless you. Make sure that you're putting 16 in those places. All right, so now we have 14 times 180 over 16. Are you guys ready to get a calculator yet? Okay, so that's the top number, right? And then we need to divide by 16. (157.5 degrees). Do not round. If you get to the homework and you end up with a decimal that keeps going, go back and simplify your fraction and write your answer as a fraction. Unless it says to round, you're not allowed to round. Does anybody want to jump up and grab a calculator at this point for the rest of the notes, or are you good? Okay. When you come in from here on out, though, make sure you guys grab one because you'll want it. As the lessons get harder, we're all going to need a calculator, okay? All right. So this one, find the measure of each interior angle of a pentagon. What are our key words? Each. Pentagon. Interior. All right, we got A, B, C, D, E. So here's the question I have for you. Be careful that you don't look at that word each and think, oh, I used this formula. When is this formula only able to be used? When it's regular. Is this regular? No. So we're going to have to think of a different way to work the problem. What could we do? Karina? We could sum them all, add them all together, and then what? Exactly. So we know that since this is a pentagon, it's got 5 sides, which means we know that 5 minus 2 times 180 tells us that the sum is going to be 540 degrees, right? So first we got to think about what should they all add to be. We've been used to setting them equal to 180 a lot. That's a very common mistake on this test, so be careful. It's only going to be 180 if it's a triangle. Anything else, you've got to calculate what is the sum. You might have it memorized by then. If not, plug it into the formula. And then you're going to add all of them together just like we did with triangles and set them equal to 540. So let's do that. 18 plus, I'm going to write it out, 18C plus 32C plus 32C plus 18C plus 35C should equal 540. Okay, now let's add those together. What's 18 plus 32? 50 plus 32? 82 plus 18? 100 plus 35? 135C equals 540. And then we're going to divide by 135. Oops, 135. So C equals 4. And then the question said find the measure of each angle. So then we're going to have to go back, plug 4 in for each one of those. Almost. Really, we only have to do 3, right? Because we know that B and E are the same and C and D are the same. So let's start with A. Measure of angle A was 35 times 4. How much is that? 140. Don't forget your degree symbol. Don't forget your little M for measure of your angle. Then we can say the measure of angle B is going to be the same as the measure of angle E, and those are both going to equal 18 times 4, which is how much? 72 degrees. And then we can do our C and D. So measure of angle C should be the same as the measure of angle D, which should equal 32 times 4, which is 128 degrees. Okay, so we've been doing the same thing with triangles, it's just now we've got to figure out what is the sum. Any questions here? All right, good. It is. I think you'll find that this chapter is not bad other than the properties and being able to apply them correctly. There's a few little things that may make it challenging, but it's not near as bad as chapter 5. All right, so now we're ready to talk about exterior angles. So exterior angles, remember, can be an angle. There's one angle at every vertex if you just extend out one side of your shape. So if you extend it out, you can have an exterior angle here, exterior angle here, exterior angle here. What do you notice that those all add to be on this triangle? 360. Then they give you another picture. Now we have 5-sided shape. We have exterior angles listed. If we added them all together, what does this add to equal? 360. Exactly. And we can investigate it for 4 sides. We can investigate it for 6, 7, 8, 9. But if you will just believe me right now, and then you can go home and play around with it. If you don't believe me, you can draw your shape and use a protractor and measure it. Or you can just believe me. So this one is super simple because there's no formula really other than just a fact. If it is exterior, the sum of all the angles will always add to equal 360 degrees. And if you think about it, as you add a bunch of sides and it gets really big, those sides start to look like a circle, right? And if I extend out all those exterior angles, they're going to start, when you add them all together, they're going to approach a circle. So it should always add to be 360, even when you get a ton of sides. Okay, interior can get infinitely big, but the exterior angles are always going to add to be 360. Always. Okay, so nothing you have to do there, and they'll trick you. They'll do problems like this, where they give you some picture. And then maybe they go out here and give you all these angles out here and say, what's the sum of all the exterior angles? And you start thinking, oh, I've got to add all these things together, but really the answer is just 360. How's the flashlight? Yes, ma'am. Yes. Well, I talked to Kara again just this morning on the phone, and she said it is not possible to fix that at this moment. She said she talked to him yesterday, and that he kept telling her he finally understands, And she said, again this morning, Kara said, they can't do it. Oh, my word. Okay. So I'm just entering grades then with the new dates not being last week. Does he say? Uh-huh. Oh, yes. Mm-hmm. Did he look at my grades today? Because yesterday I had them all set so that they were not posting until next week. So all of my dates, there was like a line, and all of my dates were for next week because I was afraid that it would mess things up if it was actually calculating it in. So I didn't have it where anything I'd entered was figuring in until today. And this morning I started, after talking to Kara, I realized, well, they're just going to have to do all semester, so I'll just put them all back for yesterday. Okay. All right. I know she said they looked at mine together. Yeah. Okay, that's good. I appreciate you letting me know. Yes, I'm just going to keep putting them in then for these dates, and at least I can go back and like say, okay, anything before the 11th was first 9 weeks, anything after wasn't, if they need me to. Okay, thank you. Bye-bye. Okay, sorry guys. All right, moving on. So now we're back to what if they want us to find one exterior angle, and again, this will only be if it is regular. Be very, very careful. This can only work if it's regular. And they say, what is one angle? Or again, the word problem, it might use the word each. So if I know they all add to be 360 and I want to just find one of them, what would I need to do? Very good. Take the sum, 360, and divide it by how many angles you have, which will be n. Okay, so it's the same for both. Find the sum and then divide it by n, depending on whether it's interior or exterior, and you're looking for one angle, but it has to be regular. Okay? So we already said this, it's 360, and then now we've got some more examples. So make sure you're with me here in the notes, because I've kind of jumped ahead a little bit. So flip your notes over. Okay, so now we want to, again, find the measure of each exterior angle of a regular 20-gon. What are my keywords? Regular. What else? 20. Each and exterior. Okay? Exactly. We just take 360, which is the sum, and since it said each, we're going to divide it by n. Since it's a 20-gon, we're dividing it by 20, and we get 18 degrees. Don't forget your degree symbol. Pretty easy? Okay. Kicker there is just going to have to know your two formulas. Or four formulas, sorry. Okay, here's another one. Find the value of b in the polygon. The only thing I will warn you about, be super careful. Somewhere, I don't know if it's on the review, the test, the homework, a problem in the book somewhere, but they do this on some problem somewhere. I'm pretty confident, I remember. Sorry, let me draw this first. They do this. And what students will do is they'll add these three together and set it equal to 360, but what are you forgetting? The other one. And what is the other one going to be? 90 degrees. So be really careful about if you see a 90-degree angle and they didn't extend the line on out, or even if they did, but they didn't include that angle, that you know that those two, interior and exterior, are going to have to sum to 180 because they form a straight line. Okay, so just be real careful with that. Otherwise, we can just add all these together and set them equal to what? 360. So let's do that. We've got 33b plus 16b plus 10b plus 28b plus 15b plus 18b equals 360. And again, you can make sure by, did you have the same number of exterior angles listed as you do sides? Oh, you don't want to do that. This is fine. So we have 6 angles and 6 sides, right? So we should have all the angles included. All right, somebody help me out. What is all of this added together? So we have 120b equals 360, and then we just divide by 120. Good, so b is equal to 3. And then read your directions carefully. Is this our answer, or are we supposed to plug it back in and find each angle? Just b. So don't go and plug them all in and do a bunch of work you didn't have to do. Okay? So now, watch your directions. All right. Last question, I think, in the notes is this one, correct? All right, so you guys go ahead. You and your partner, read it, talk about it, see if you can figure it out, and then we'll check it. I will tell you that the one thing I don't like about this problem is that they make you assume that this is regular. Pentagons do not have to be regular just because they're equilateral, but it should have had these angles marked. So it is regular. You can use that assumption.
And then one is at the.
Mhm. Yes, one is pointing to this angle right here. Okay, so there's a couple of ways you could have looked at this. I'm hearing 72 degrees from several different people. The easiest way would be to say this is an exterior angle, and this has 5 sides. So if I want to know one of those exterior angles, since it's regular, I could just do 360 divided by 5, and that goes in there 72 times. The longer way, which is still valid, is you could have said, okay, let's find this angle, and what do we know about an interior and an exterior? They're always supplementary. So you could have said 5 minus 2 times 180, which is 3 times 180, which is 540, and then you could have divided that by 5 to find out what is each angle. Oops. So it's going to be 108. Sorry, I'm trying to go really fast. So this would be 108 degrees, and then you could have said, okay, these two have to add to be 180, so that makes angle 1 72 degrees. Okay? But it works either way. Molly? Where are you getting 10 from? So when we define what is the definition for an exterior angle, it is defined to be the angle formed by extending one side of your polygon, not both sides of your polygon. So anytime you have that shape, you can't say I'm going to extend this side and this side. Okay? That's just the definition of an exterior angle. So one or the other. They're vertical though. Here, notice they'll be the same measure, but you're only going to extend out one side or the other side. Everybody good? Okay, let's shift to 6-2. And this is where we actually start talking about one of our special quadrilaterals. And this is where the rest of chapter 6 is focusing on only quadrilaterals. Okay, so 6-1 is any kind of polygon. Now we get to 6-2 and we just talk about the four-sided shape. So this section is all about the parallelogram. We're going to prove and apply properties of parallelograms, and we're going to use those properties to solve problems. So on your property sheet that you're creating, you're going to want to title this parallelogram, and everything we learn about the parallelogram we're going to list, okay? I'm sorry. Ashley? You just called to say hi. It's good. Bye. Call the room. Okay. Here we go. So parallelogram. First of all, we're going to learn the definition for parallelogram. And so we're going to learn the definition. That's going to be our first property of our parallelogram. And you are going to need to know it as the definition. When we get to the proofs, you will list it as definition of parallelogram. Okay, so this first property you have to know is the definition. A parallelogram is a quadrilateral with two pairs of parallel sides. I like to write it as opposite sides parallel. So not just two pairs, but the ones that are opposite are the ones that are parallel. So the definition is our first property. And it is that it has opposite sides parallel. Every parallelogram will have opposite sides parallel, and that is its definition. It is a quadrilateral with opposite sides parallel. Okay, when you write the name of a parallelogram, you will use this parallelogram symbol. Just like when we named a triangle, we always put the triangle symbol. You can only use that symbol if you know for sure it is a parallelogram. So for example, we could call this parallelogram ABCD. Again, when you name any polygon, make sure you're going in a circular motion. Do not name it ABDC because that does not form the shape you're looking for. So consecutively around your shape in a circular motion. And then we know that it has opposite sides parallel. Make sure you use those parallel marks. Look for those things in pictures to identify whether or not you have opposite sides parallel. Okay, first property. Second property of a parallelogram is its opposite sides are congruent. And we're just going to be listing these in our proofs. You're not going to need to know the name of something. You're just going to put in a parallelogram, opposite sides are congruent. So number 2, opposite sides are congruent. If it's the definition, you'll put definition of parallelogram. Otherwise, you're just listing the property. In a parallelogram, opposite sides are congruent. Okay, so again, we can mark that with congruent symbols. The opposite ones will be the same. Next properties. In a parallelogram, its opposite angles will be congruent. So number 3, opposite angles are congruent. So that will mean B and D are congruent and A and C are congruent. The ones across from each other will be congruent. In a parallelogram, the next property is consecutive angles will be supplementary. Think about that. If these two lines are parallel, what are these two consecutive angles called? Same side interior. And these two? And then if we switch gears and look at these two parallel lines, what are these two consecutive angles? And down here? So any two consecutive angles are really a pair of same side interior angles, and so they're always going to be supplementary, same side supplementary. So the fourth property of a parallelogram is that consecutive, C-O-N-S-E-C, consecutive. Consecutive angles are supplementary. Okay, so that means we're going to add to be 180. Any two that are side by side will add to be 180. And then the next and last one that we're going to list here for our fifth property of a parallelogram is that the diagonals will bisect each other. Does not mean the diagonals are congruent. It means that where they intersect, they split each other into two congruent parts. So BZ and DZ would be the same, and then AZ and CZ would be the same. But they're not all four the same. Okay? So they bisect each other. So number 5, diagonals will bisect each other. Okay, so 5 properties that you're going to have to memorize, and then basically we're going to be applying these properties to some problems. The first one's the definition, opposite sides are parallel, parallelogram, and then everything else is just a property. Okay, so they give us, this is a parallelogram because when they named it, they put the symbol for a parallelogram. So that means we automatically know all 5 of these things are true. Okay? They want us to find the distance from C to F, which would be this side here. And they tell us what that will help us. Okay, they tell us DG is 31. What else do they tell us? Okay, they tell us DE is 74. So what do we know about the opposite sides? They are congruent, so that means that CF should also be 74 millimeters. And just like those first questions on the Chapter 5 test where it was pretty easy answers, there wasn't a whole lot you had to do, you'll have questions like that in Chapter 6 where they're just pretty simple as long as you know the properties.
So if this is good, we have to figure out what we put definition or say that opposite sides are?
We would say in a parallelogram, opposite sides are congruent. Okay? All right, keep going. I think it's the same picture next, but then a different thing they ask you to find. Is that correct? Yes. So now they want us to find the measure of angle EFC. So find E, F, and C. We're looking for this big angle. What do they give us that helps us? Okay, so they tell us FCD, which is this angle, is 42 degrees. So what do we know about those two angles? Okay, so consecutive angles are supplementary. They're consecutive, which means they add to be 180. So we just do 180 minus 42, and we get 138 degrees, right? Are we good? Okay. Memorizing these properties, though, because you're going to have to justify and write proofs, and so you need to know what your properties say and what's true about them. All right. Same picture. This time they want DF. This whole length from D to F. What do they tell us that will help us? Okay. DG is 31, and what property are we going to use that's going to help us? Okay, number 5, diagonals bisect each other. So if that's the case, then GF is how much? GF is 31, so DF is 62. And don't forget your units, millimeters. Okay, pretty easy, right? As long as you know your properties. And it's really easy when all we've learned is the parallelogram. Before the end of this chapter, we're going to learn parallelogram, rectangle, rhombus, square, trapezoid, kite, and isosceles trapezoid. So we will have 7 shapes with 7 sets of properties that you're going to have memorized by the end of chapter 6, and it's quick. We do 6, 1, and 2 today, 6, 3, and 4 on Thursday. We'll come back on Monday, do 6, 5, 6, 6, and that's the end of the chapter. We will review on Tuesday and test on Wednesday. It is super fast, okay? So study this week your properties, because when we hit Monday, it's in the lesson, review, test, okay? Test will be Wednesday, because Monday we'll finish the chapter, Tuesday we'll review, Wednesday we'll test. Okay, so it's quick. Okay, next one. We know this is a parallelogram. We want to find YZ. What can we do here? What property could we use?
YZ.
Opposite sides are congruent. YZ and WX should be the same, so we can just set those equal. 6a plus 10 equals 8a minus 4. Solve for a. Okay, I heard add 4 first. So add 4 to both sides, and we get 6a plus 14 equals 8a. Subtract 6a. 14 equals 2a, so a equals 7. And then the question said find YZ. So let's plug it back in. 8 times 7 minus 4. Yes, multiply 56 minus 4 is 52. So YZ would be 52. And again, way back from chapter 1, do not put a line segment above it when you are giving me what its distance is. Okay, any questions there? Okay. So next, are we ready for proofs? No, not yet. All right. Another problem here. Again, this one wants us to find angle Z. Which property can we use? So number 4, consecutive angles are supplementary. That means we're going to do what with these two expressions for angles? Very good. Add them and set them equal to 180. So 18b minus 11 plus 9b plus 2 equals 180. All right. Combine like terms. What's 18 and 9? 27b. Negative 11 plus 2 minus 9 equals 180. Add 9. Very good. Divide by 27. 7. Okay, so B is 7. The question, though, said find angle Z, so let's go back and plug it in. Measure of angle Z will equal 9 times 7 plus 2. 65 degrees, because we have 63 plus 2, which is 65 degrees. Don't forget your degree symbol. Don't forget your little M's for measure of angle. Yes. All right. So now we're going to start looking at some proofs. And here's the thing. And there's an example before that's not proofs. But when we get to the test, the best advice I'm going to give you for studying for the proofs on the test will be to go back and look at the ones in your notes and the ones you have on your homework. I'm not going to give you a bunch of other examples to practice, so the ones on your test will be very similar to the ones we do in the notes and the ones you do on your homework. So if you really want to do well on the test, make sure you go back and practice the ones in your notes and on your homework, okay? All right, so we've already said this. I'm going to skip this slide and go straight to this one. This is not a proof. It says 3 vertices of the parallelogram are given. Find the coordinates of vertex M. So I gave you a graph that's already got 3 of them graphed for you, right? Okay. And I would expect on the homework that you could graph those 3 points. Just make sure you don't mess up graphing a point because it'll mess up your whole problem. So we know J, K, and L, and we're looking for where would M have to be so that this is a parallelogram. We want specifically where it would need to go. So what could we do? Connect your dots. We know for sure it's going to be... Okay, so I'm going to come back to you real quick, Edwin. Be careful that you connect your dots to match your name, though. Sometimes I have students who connect like J to L to K, and that's not how they named it. So be real careful that you are connecting it as J, K, L, and you're trying to find M. Okay? So Edwin said we could find the slope from K to L. And what should we do with that slope? Where? Okay, our opposite side should be parallel. So if we find the slope from K to L, then J to M should have the same slope. Well, as long as you don't reduce your slope, that will take care of the distance piece. So if you have something like 6/4, don't reduce it to 3/2, or you've shortened the length of the line segment. So leave it 6/4 when you're counting your rise over your run. Does that make sense? So let's do that here. What is our rise and run from K to L? Okay, 4/4. So don't reduce it to 1, because if you do, then you're only going to go up 1, right 1, and think that M has to be right there. And that's not true, right? So if you don't reduce your slope, you should just be able to repeat that slope. Up 1 or up 4 and right 4. And so it turns out to be 7 what? 7 -4. Everybody agree? And so the answer would be M is at 7 -4, and circle your answer. Make sure that it does connect and look like it's a parallelogram. If it doesn't, you know you've done something wrong, go back. We could have also done the slope from J to K and repeated it where? At L, or K to J, I guess. From K to J, then we could have went to L and repeated that slope. So it doesn't matter. K to L was a little quicker because it was shorter. All right, now we're ready for some proofs. We are. Because this is the kind of stuff that you enjoy doing. If you had to do proofs, these are the kinds of proofs that you enjoyed doing, I promise. Because look at what we're trying to prove.
Oh, good.
See, I told you. We're trying to prove triangles congruent. So let's review real quick. Yes! I knew it. You're going to fall in love with proofs. So what are our 5 ways to prove triangles congruent? SAS. What else?
ASA.
ASA. What else? SSS. HL. That does not prove triangles congruent. SAA or AAS, and you can write it either way.
No bad words though.
No cussing at me, okay? No dyslexic butts in here. All right. So I'm glad you did bring up CPCTC, though, because that is used after we prove them congruent if we need parts congruent, right? So that could show up if we were trying to prove something beyond proving them congruent. You got it. All right, so we want to prove our triangles congruent, but obviously it's going to be related to these properties we just learned, that we're trying to get the 2 triangles congruent because now we know it's a parallelogram. So if it's a parallelogram, we know all 5 of these things. Our goal is to prove which 2 triangles? AEB.
And C.
All right, so we want the left and right triangles, right? So we're going to try to get some information about them that would lead us to one of these 5 ways, and then we can say the 2 triangles are congruent. So I've given you the statement of reasons box, right?
Oh, this is fun. This proof is fun. This is
Okay.
fun.
There's a lot of ways we can do this, so let's just start with some ideas. What are things that you notice we could mark, that we could write down? Okay, say it again, Edwin. AB and CD. Okay, we can say they're parallel. If we say they're parallel, okay, but if we say they're parallel, how will that help us get some information about these 2 triangles? Okay, I'm going to come back to that, but if we say they're parallel, what could that tell us that would help us in the triangles? So if we write down what Edwin said, that these are parallel, they're cut by a transversal, and so now what would be congruent in my picture? Alternate interior angles. So you could definitely write down that those are parallel and then use alternate interior angles. We could also say what, Sarah? That they're congruent, because in a parallelogram, opposite sides are congruent. There's going to be a lot of different ways to get to your goal, is what I'm trying to point out, and that you may all have different ways to get there, okay? What you don't want to do is write down everything you know, because your proof is supposed to be a logical step-by-step process. So as soon as you have enough information to say the triangles are congruent, you should stop. Don't keep listing things just because you know it's true, okay? So I'm going to start with what Edwin said since I heard him first, and say AB is parallel to CD. It is not, actually, I'm sorry, we do need to write down our given. Thank you, Javi. I can't say that because I don't have my given listed. Thank you so much. Number 1, how about ABCD is a parallelogram? Because we can't say opposite sides are parallel until we know it's a parallelogram. Yes, parallelogram symbol. Okay, now we can say AB is parallel to CD. And what's going to be the reason, though? Definition of parallelogram. When we say the opposite sides are parallel, that comes from the definition. So definition of parallelogram. Okay, so now that they're parallel, yes, ma'am? Yes, I'm so sorry. Man, like I have messed up twice. I don't know. That's why I won't be here tomorrow. AB is parallel to CD. How about segment AB, segment CD? All right, so now we can do what Alexis said, and we can use those alternate interior angles and say that those are congruent. So now we have angle B is congruent to angle, can I call it angle B?
No.
Nope. How do I need to name it? Very good, Karina. Because there's 2 angles there at B, I cannot use one vertex, so angle ABE is congruent to angle CDE. Okay, and that was by what theorem? Good. Alternate interior angles theorem. Now, we could go on to something different, or we could say something else at the exact same time using the exact same reason. Do you guys see that this line here? Right. I could use the same parallel lines, but the other transversal. Do you see that? And this angle here would be congruent to this angle here, right? Okay. Don't have to. I heard somebody say vertical angles. We could use vertical angles instead. There's several ways about it, okay? But since I've already written down this reason, do you guys want to go ahead and just name the other pair of angles?
Yes.
Okay. So In statement number 3, then, we'll list the other angles. How do you want to name them? BAE, I heard. Angle Bay is congruent to angle DCE. Oops, DCE. Okay, and it's the same reason. So now we have 2 angles congruent. What else do we need? Careful, we don't have sides congruent. We only have sides parallel.
Well, opposite sides are congruent because it's a parallelogram.
Okay, so hold on, I'm going to come back to you. I love that Ridley said it, though, so we can get our minds there. We could do vertical angle theorem, but that would give us angle, 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 and that's not a way, right? So we could have used vertical angle instead of alternate interior, but we don't need vertical angles now. So what are we missing that we need to mark that we could say? Okay, a side. So which one of these properties do you want to use? Okay, I heard 2 different things there. We could do diagonals bisect each other. If we do that, though, be careful.
No, we'd have to find another angle because you could just do A.
We've got 2 angles. We just need a side now. Okay, hold on. We have lots of ideas going on. Let me go back to what Katrina said, okay? She said we could do diagonals bisect opposite, or diagonals bisect each other. So we could say this side's congruent to this side. And that would give us angle, angle, side, which would work. Or we could say this side's congruent to this side, which would give us angle, angle, side, which would work. Or, I heard somebody say, we could do opposite sides congruent. If we did that, we could mark this side congruent to this side, and now we have angle, side, angle. It does not matter. You pick. But you don't need all 3. You just need 1 set of sides. It's going to change what your reason is at the end, though. So which one do you guys want to do? Diagonals bisect opposite, or bisect each other, or opposite sides congruent? Okay, I heard opposite sides congruent. So number 4, I'm going to come up here because I'm running out of room. We can say that AB is congruent to, very good, way to name it correctly, CD. But that does not come from the definition. The definition only says opposite sides are parallel. It's a property of a parallelogram that says the opposite sides are congruent. Okay? So this would be as our reason. When you write this, you need to say in a parallelogram, and you can use the symbol, opposite sides are congruent. Because remember, we're going to have 7 different shapes, and there's different properties for every shape. So where do we get this from? In a parallelogram, opposite sides are congruent. And now we can say, number 5, that triangle AEB is congruent to triangle CED. And since we chose this method with the 3 marks, that gave us angle, side, angle, right? So it would be angle, side, angle. All right, we've got 1 more we need to work through. And it's not hard, but we only have 5 minutes. So we're going to have to go quickly. Yeah, we could have done diagonals bisect each other and opposite sides, and we would have had side, side, side.
That would have been easier.
Mm-hmm.
Why didn't you do that?
Because you said opposite sides are parallel, and I went with you, Edwin. I hear you, but I'm going to tell you that this was very important for the test right here. So if you leave right now, you need to make sure you watch the video, because this very proof is very much similar to questions on your test. Yes, your assignment is just this worksheet, all problems. Front and back, every problem. Okay, quickly, guys, we only have 5 minutes, and I'm telling you, you need to know how to do this, okay? So I need us to focus really quickly. Okay, so GHJN and JKLM are parallelograms. H and M are collinear, N and K are collinear. Prove that angle H is congruent to angle M. So we're going to start with number 1, listing all our given. And for time purposes, I'm going to circle it and point right here. Yeah, it's your notes. Given. Okay, look at what we're trying to prove. H congruent to M. We want to get this angle congruent to this angle, and we don't know that yet. So you shouldn't really mark it, but I'm going to mark it just so we can make sure. Okay? We know that these are parallelograms and these are parallelograms. Okay, so here's some ideas. I want you to think about something we learned way back that talked about if two angles are supplementary to two congruent angles, then those angles are congruent to each other. Do you remember the name of that theorem? If two angles are supplementary to two congruent angles, then those angles are congruent to each other. Congruent supplements theorem. I want you to think about that because that's the easiest way to do this proof. We could do it a different way. It's going to be a lot harder. So the easier way is to say, if we know these are parallelograms, then angle G should be congruent to which angle? Angle J. And angle L should be congruent to which angle? Angle J. Right? And we know that these two angle J's are going to be what? They're going to be congruent to each other, right? Because they're vertical. Okay, and what do we know about these two angles? They're going to be supplementary. And what do we know about these two angles? They're also going to be supplementary. So if these two angles are supplementary to these two angles, and we can prove that they're congruent, then that means these two have to be congruent. And that's that congruent supplements theorem. So let's see if we can write it down in the time we have left, okay? So number 2, we said angle G had to be congruent to angle. Let's name that angle J. How do you want to name it? Angle HJN. And for the same reason, we have angle L is congruent to what angle? Okay. Okay, we can do MJK. All right, and the reason for that was in a parallelogram, opposite angles are congruent. All right, and then we said that those J angles are congruent to each other because they're vertical, right? So we need to say angle HJN is congruent to angle MJK. I'm just naming those two J angles. And that was by what? Vertical angle theorem. And so if G is congruent to HJN, but HJN is congruent to MJK, and MJK is congruent to L, we can say that what? We could. So we could do a step in between here that says if G is congruent to HJN and HJN is congruent to MJK, or I think what you said, sorry, angle L is congruent to MJK, MJK is congruent to HJN, then we can say what? HJN is congruent to L. Good. What did you use to get there? Transitive. So angle L is congruent to angle HJN by transitive. Property of congruence. L is congruent to HJN. And then notice now we have HJN's congruent to L and HJN's congruent to G. So what does that mean? L is congruent to G. And if L is congruent to G, how did we get that? L was congruent to HJN, G was congruent to HJN, so L was congruent to G by transitive property again. Just did the same thing again. Transitive property of congruence. And then we have left, we haven't said yet that these angles are supplementary and these angles are supplementary, right? But we do have G and L now congruent. So the last things, and I will go back over this on Thursday and we'll finish it, okay? But the last things would be to say they're supplementary and then congruent supplements theorem. But we'll finish it on Thursday.